Okay, but you can tell me a little bit later what VOD friends is. And if you have any comments as well, then just let me know. Okay, let's get started. So on the right side of the board, these are some of the things that I want to cover today. Some of them we began last class, and then some of them will be new for us. So we started talking about the cobweb diagrams for the logistic map in the last class. Now we're going to talk about this important concept of a bifurcation diagram, which we're going to draw here and also show you done by Matlab. I'm going to more concretely or more rigorously define what a fixed point is and what a two-cycle is, and we're going to relate that to the logistic map. And these two form homework problems. We're going to give a threshold for stability. How do you check whether a fixed point is stable or unstable? We're going to talk about stability for two cycles, and then you can extend that to n cycles. And then we're going to talk about more rigorous concepts of stability, more clear definitions of what stability means. And stability is a bit of a tricky concept, even though we've mostly been using it in an intuitive manner. Okay, so let's switch now to Matlab. And I want to remind you what we did with Matlab last time, which was we just used Matlab to do these types of cobweb diagrams in an automated fashion. Okay, so this was the logistic map. You remember it looks a bit like a parabola. It is a parabola. It has a max at x equal to 0.5. And essentially what we did with Matlab was we started off with kind of almost random values of the initial condition, 0.2 here, and then we used Matlab to do the cobwebbing. And what we noticed was that when mu here, the parameter in the logistic map, gets to be quite large, and in particular above the value of 3, here 3.65, then the orbits of the dynamics, or the orbits of the system, become a lot more complicated, right? So this picture here on the top is plotting the iteration number n versus xn, and you notice that now is looking a lot more complicated. Okay, so what we want to do is we want to somehow understand the structure of these long-time solutions. So long-time solutions, I mean that you're going to run n for a long time, and eventually it's going to settle down to a state. And what you're interested in is that, what is that state? Is that state a single point? Does xn converge to a single fixed point as n goes to infinity? Does it converge to 2 points, that it jumps back and forth between 2 points? Does it converge to a 3-cycle, 3 points, 4 points, 5 points, or something else? Okay? And this is what we want to do with this next code. And I'm not going to explain the code, I'm not going to explain the exact details of the code because it's a bit long, but I'll explain to you intuitively what the code is trying to do. What the code does is that it runs between two values of mu. So firstly, it goes from -2 to 4.1 in mu, and for each value of mu, it's going to so even though it goes, you see -2 and 4.1 here, actually we're just going to run from 0 to 4.1. We're going to do the positive values, and I'm not going to show you the negative values because this is a little bit later on in the code, and it takes a little bit of time to run to line 43 or where you see this. Okay, so we're going to run from mu is equal to 0 to mu is equal to 4.1 or thereabouts. And for each value of mu, you're going to basically start the simulation at 0.1 and then run about 1,000 times, or 500 to 1,000 times. N will run to 1,000 in terms of iteration. So you're going to calculate x1, x2, all the way to x to 1,000. Okay, and what you're trying to do is you're trying to collect eventually what the steady state is. So you're going to ditch the initial behavior because you're not so interested in the initial behavior. That's the initial transient that we explained before. And then you're going to plot where it hits after a certain number of runs. So this is what they call this burn-in period. Okay? And so just to give you an example, suppose that it's a fixed point. There's a single fixed point that the system will approach if you plot that fixed point, you would just land on a single point here. If instead you approach a two-cycle, that's to say that you're approaching a configuration where you're bouncing back between two numbers, then you should see the dots hit 2 points. Okay, so let's run this, and it takes a while to run, so we're just going to run it, and I'll explain it in the background. And it's taking a long time to run, in particular because my computer is really dying with the amount of video recording and simulations I'm running at the same time. But okay, so you see mu is starting from 0, and then it starts to increase, and we're going to run to 3.5 or 4. And each dot that you see is the result of many, many simulations or many, many iterations of the map. But in this case, when mu is less than 1, even though you start at 0.1, those iterations will eventually converge to the fixed point at x equal to 0. So this picture, you're only seeing x equal to 0. This is the lone fixed point in the system. Okay? Now you'll remember that when we did the cobweb diagrams by hand in the last lecture, when mu increases past 1, what happens is that the parabola then intersects at another point. So in addition to x equal to 0, it intersects at a fixed point for x positive. And this is now what you're beginning to see. That fixed point with x non-zero, there are two fixed points in the problem now, one with x equal to 0 and one with x not equal to 0 and positive. That fixed point is stable, so all the simulations all the iterations rather, are converging to that value of x. This is a stable fixed point. Okay? And this is going to continue, it's going to continue, it's going to continue. Now, again, remember when we did the cobweb diagram on Wednesday, that eventually the gradient of the second intersection point is large enough that the orbits will no longer converge towards it, but actually they started moving away from it. It went from being stable to unstable, right? And at that point, what can happen is that you have not just a single fixed point in the system, but you have the possibility of a two-cycle, of 2 points in which the configuration bounces back and forth between. Okay? And it's taking a while to get there, but we're going to have to wait for it to get there all the way to 3. While it's waiting, I'm just going to go back to the board here, and I'm going to draw exactly what I've been trying to explain. If the video is a bit choppy, I'm afraid there's nothing I can do about it. So this is what we call the bifurcation diagram. So this is the bifurcation diagram, okay? And in the bifurcation diagram, on the horizontal axis, you plot mu, and on the vertical axis here, you plot the fixed points of the system. If you can't see what I'm writing here, it says fixed points, and you'll plot as well the end cycles and so forth and so on. The point is that when mu is sufficiently small, right, so let's do 1 here, 2 here, and then 3 here. You remember the picture of the cobweb diagram when mu is sufficiently small was that here's the line y is equal to x, or f is equal to x, and the parabola for the logistic diagram was below that line. And everything was driven towards the fixed point at the origin, right? So in this case, there's only one stable point in the system, and it's the line x equal to 0 here. So this is the fixed point, x equal to 0 is the fixed point. Okay? Now, above 1 here, then the cobweb diagrams would change, right? Let me now, the simulation is done. I'm just going to quit it. Okay. Above 1, this cobweb diagram changed, and then now the parabola was above the line f is equal to x, right? And so you've introduced another fixed point here. And notice, by the way, we haven't drawn the transition, but actually, if we were to draw the transition between these two states, this fixed point here emerges from outside of this of this intersection. So the parabola is firstly like this, and then it gets a little bit larger, and it gets a little bit larger, and so forth and so on, right? So this fixed point here, you have to think about it, but this fixed point is coming out of the x equal to 0 point, right? So this x equal to 0 point will continue, of course. It's, in fact, I'm not going to draw it with a solid line here. In fact, I'm going to draw it with a dashed line. This fixed point is still there, but it's unstable, so that's why you don't see it in the code that we just ran. And you've introduced another fixed point which comes out of the system like that. Okay? Now we have to get the equation for this fixed point, which we will in a minute, but this is the other fixed point. So I'm going to write this as x equal to, in fact, the other fixed point is at 1 minus 1 over mu. This is it's a fixed point here. Okay? X equal to 0 is always a fixed point, so it always exists, and we're going to use this terminology of solid for stable and dash for unstable, like that. So x equal to 0 goes from stable to unstable, right? And then the other fixed point emerges. Sometimes, by the way, for stability, you can also draw little arrows here. And the little arrows mean that if I were to start at a value of x, which is slightly away from 0, at this slightly positive value, is going to be driven to the other stable fixed point here. So if I did want to do arrows, I would do arrows pointing towards the fixed point from below and then down from above, right? So that's a stable fixed point. Okay, so now mu gets still larger, and eventually this gradient, as we drew last lecture, this gradient becomes large enough so that the orbits start to move away from that fixed point. This fixed point transitions from being stable to being unstable, okay? But the fixed point is always there, and so we're going to draw a dash like this. It's always going to exist. It's always, it's still there, the fixed point, but the point is that even if you were to start near it, you'd be moving away from it. Okay, so here's the trick, right? You see, this is a dashed line and this is a dashed line, so these are both unstable, right? But the system has to approach some configuration, right, between the two of these. And the question is, well, what does it approach? And so you would rationalize that it has to approach two states. This is, let's call this x1 and x2. This is our 2 cycle. Okay. Now, in a minute, I'm going to show you the Matlab simulation. And in the Matlab simulation, you're not going to see this dashed line, because the dashed line, you would never get it, right? You're always unstable from that. So even if you did your iterations, you would never converge to this dashed line unless you start exactly at it. And even if you start exactly at it, then there might be numerical error that would take you away from it. But the point is that if you were to start at any state between the two, you would then approach a state in which you're jumping back and forth between x1 and x2. Okay? Let me erase a few things. Okay. So the question is, what's going to eventually happen to this system? And what's going to eventually happen is that this is going to then split into a 4 cycle and an 8 cycle and so forth. It's going to get very, very complicated, right? And it's going to end up splitting faster and faster. So you don't have to wait all the way to 4, for instance. It's going to split a lot earlier than 4, and then it's going to start doubling and doubling and doubling, and it's going to get very, very complicated. That's one thing to keep in mind. The second thing is that these transitions here, these special intersections, are called bifurcation points. This is called the bifurcation point. And this is called the bifurcation point as well. And then I suppose we're going to have to write down the exact definition of what a bifurcation point is, but for all we care about for the moment, a bifurcation point is a special point in mu so that the stability of the system changes. And notice I've not defined yet what stability is, we're just taking it intuitively. Some key condition in the system changes. This is our bifurcation point. And this is essentially what we're interested in trying to understand. I mean, effectively the course is about trying to establish these kinds of bifurcation pictures, because these bifurcation pictures explain a great deal about the system. Okay? Okay, so this is the key concept of the bifurcations and also of the bifurcation diagram. A bifurcation diagram is this, for our case, this diagram of mu versus the fixed points or the cycles in the system. In next week's lectures, we're going to define exactly what are the types of these bifurcations. How do we classify what is the difference between this bifurcation here, which looks a lot different than this bifurcation here. Notice in this bifurcation here, you had a fixed point which continues and transitions from stable to unstable, and that you have the creation of a new fixed point coming out. This one looks a little bit different. This one you have a transition between a stable and unstable, solid and dash, and then a 2 cycle coming out. Okay? Let me now show you the Matlab picture. So this is the Matlab picture of our simulation, and I was explaining exactly what the construction of this diagram. From 0 to 1, you have a stable configuration. And then after this mu is equal to 1, it goes unstable. It's a dashed line, but as I said, you're not going to see the dashed line in these simulations because it's unstable. You have a fixed point which comes out, and that fixed point, again at mu is equal to 3, goes to be unstable. And so you don't see it in the diagram, but you would, indeed, if you were to do this on paper, you'd draw it out. It'd be a dashed line here, and it splits into a 2 cycle. So the simulation is basically bouncing back and forth between these 2 points. Eventually, if I can figure out how to zoom in here. Matlab's being a bit slow, it's not allowing me to zoom in. But if I were to zoom in to this point where the mouse cursor is, you would see that eventually at some value, let's say 3 point, I'm not sure the value, between 3 and 4, at this critical value, the 2 cycle also splits. The 2 cycle are these two forked arms. Those split, and now you have a 4 cycle. And then it gets more and more complicated. It keeps on splitting, and you get more and more cycles. Okay. Sorry, I'm not able to zoom in and zoom out because everything has slowed down to a crawl. Can there be an odd number of cycles? A very good question. Let's delay the answer to that to later. In the logistic equation, no, there can't be. But yeah, you can certainly have odd number of cycles in other systems. The 2 cycles and 4 cycles, etc., are they considered to be stable? Yes, so you still have the notion of stability even though you have a 2 cycle. So you can still define stability even if it's not a point, right? So you'd say that it's stable because you're always close to one of the 2 points of the 2 cycle or one of the 4 points of the 4 cycle. Okay. All right, so we've covered item 1. Let's go on to item 2 and item 3 and so forth. And this is something that you should read in your lecture notes. I'm embarrassed that I don't know the exact chapter that it is in the lecture notes, but I promise that I'll try to be a bit better in the future and give you the references. Okay, so item 2. Item 2 is that the fixed points is at x equal to f of x for the logistic equation. Okay, and so you put in the value for f of x, which in this case mu times x times 1 minus x. You can go ahead and remove the root of x equal to 0. That's always a fixed point in this system. Or the other one, once you solve it, you move the x and then you move this this term over to the left-hand side, you'll find it's 1 over 1 minus mu. So these are the two fixed points of the system. Okay, and you'll notice that this one here only has x greater than 0 if mu is greater than 1. Okay, but the point is that for all values of mu greater than 1, this one always exists, and it just gets closer and closer to 1 as mu goes to infinity. So you always have two fixed points in the system when mu is greater than 1. If mu is less than 1, then this one here is not on the relevant side, and you only have x equal to 0. Okay? So that's how you find fixed points. And in the homework problems, you're given a certain number of maps. In the first question, you're asked to just reproduce this calculation and then discuss the results for the logistic diagram. In question 3, you're asked to get fixed points for other problems. Okay, let's talk about now two cycles. How do I get the equation of the two cycle? This is more complicated. So item 3, to find two cycles, what you need to do is you need to solve x equal to f squared of x, or f of x. So you remember that whenever you see f to the n here, that means composition, it doesn't mean power. So that's the definition of a two cycle. You hit it once with f, and then you hit it again with f, you come back to yourself. When you solve this equation, you should also end up with the solutions of the one cycle, of the regular fixed point, because a one cycle is, it will also satisfy this definition. Okay? This equation is more difficult to solve. So you have to put in f of x here, so we'll do it in two steps. So put in the logistic map, mu times x times 1 minus x. And then this input here is then placed inside the same formula. So this is mu times, if I want to do brackets here, mu times x times 1 minus x. And then another bracket, 1 minus mu times x times 1 minus x. Okay, so it's just a logistic equation, but the input is now itself. Mu times x times 1 minus x. Okay, and in the homework, in the problem set question, I've asked you to solve this equation. Now, this is a quartic equation, right? You're going to have to expand this whole thing, and you get x to the power of 4, and it's a pain to solve that. But I point out in the problem sets the trick to solving it. And the trick is basically that this here is a quartic polynomial. Okay, so firstly, expand everything out. It's not so bad to expand. Expand everything out, and then make the power x to the 4, the term with an x to the 4 in there, make that a 1, just for simplicity. Just divide it out of the equation. And you want to compare this with, now you know that whatever equation you get here from the quartic polynomial, it has to have the two roots that we found previously for the fixed points in there, right? It has to have x equal to 0, and it has to have x equal to 1 minus 1 over mu, because those fixed points are themselves solutions of this quartic polynomial. So you just have to compare that with x times x minus 1 over mu. I say just, it's actually a little bit of a pain to calculate. And then x squared plus ax plus b. So you know that whatever quartic polynomial this is, properly normalized, so that the leading, you'll notice the leading x to the 4 here has a coefficient of 1. Whatever quartic polynomial it is, it has to be placed in this form. It has to have x equal to 0 as a root, and I've written this wrong. You'll probably notice in the chat in a minute. But this is x, and then this is x minus 1 minus 1 over mu, like that. Okay? this has to satisfy the same quartic polynomial, so all you have to do is find the values of a and b, expand this second line out, or the second to last line out, find the value of a and b, and then once you found the value of a and b, you have to solve that quadratic, and you'll get the two roots that you haven't found before, and those two roots correspond to, say, x1 and x2, which are the two elements of the 2 cycle. Okay? You can imagine that to get a 4 cycle, or to get a 6 cycle, or if there did exist a 3 cycle, it's a lot harder, right? Because you need to solve a higher order polynomial to get that. So even for the 4 cycle, it's a bit of a pain because you have to solve that equation. Okay, good. Any questions? Feel free. All right, so we've covered how to get the fixed points. We covered how to get the 2 cycles, and you know, let's talk about stability. Or at least, so stability we cover in 4, 5, 6, right? But for 4, I just want to give you the criterion, the basic criterion that you'll use everywhere for stability. The claim is that it's the gradient of the function that determines stability, right? So if this was the line x, then it's the gradient of that function which determine whether you're going to spiral in or whether you're going to spiral out of the function. If the gradient of the function was very, very shallow, if you had a very, very shallow, let's just try the picture. Let's do a proper picture here. So we take a function which has a fixed point at this location, but it's very, very shallow at that location, has a small gradient at that location. And then if you were to do the cobwebbing for that diagram, let's start here. You notice it spirals in, right? And so this would be a stable fixed point as we've drawn it. However, if the local gradient of the function is very, very steep, instead it's like this, then you'll notice that you spiral out. And so it's the gradient of the function, it's the local gradient of the function which determines the stability of the dynamics, okay? And it's tricky what happens at 1. At 1, you have to analyze it a little bit more closely. If the gradient is exactly 1, then you have to analyze things a little bit more closely. Item 4. The threshold of stability stable versus unstable can be found via the magnitude of f prime of x star if x star is your fixed point. If that magnitude is less than 1, you're stable. If it's greater than 1, you're unstable. If it's equal to 1, you got to look a little bit more closely at it. Okay? So that is, if this gradient is less than 1, it's stable. If that gradient is greater than 1, you're unstable. And if you're equal to 1, then it's undetermined. It's this order. You have to look a little bit more closely at the higher derivatives, or you have to do a little bit more careful analysis if it's equal to 1 exactly. Okay? Okay, let's show this. So let's consider x star such that x star is equal to f of x star. So let's say our x star is our fixed point. And so basically what we do is we say, I'm going to go really close to the x star. I'm going to say x star plus some delta. Then I'm going to see what happens when I put the x star plus some delta into the problem, right? Basically, when you put x star plus delta, Do you get bigger than x star plus delta, or do you get less than x star plus delta? Does it go unstable, or is it stable? Right? So we're going to let x be x star plus some delta. Delta is small. And let's let this be n. Okay? So on the nth iterate, we're going to stick in our fixed point plus delta n. And delta n is small. This is what's called linear stability. Okay? Then xn plus 1, we're going to write xn plus 1 as x star plus delta n plus 1. This is just notation, right? We're defining this to be the case, that we always write the value at the current point as a perturbation, as a distance away from x star. And then you stuff this into the equation. This is now x star plus delta n. Okay? But this one here you can expand using a Taylor series. And next week we're going to go a little bit, a bit of a review, because I know that some of you might not be used to working with Taylor series. But for now, the point here is that when delta n is small, you can approximate this as x star plus delta n times f prime of x star plus dot dot dot. So these are HOT, higher order terms. Okay? But I know that x star is equal to f of x star. Right? So I know this one is equal to that one. And so therefore I conclude that delta n plus 1 is approximately delta n times f prime of x star. But I know how to solve these types of problems. These are recurrence relations. Right, so for instance, delta 1 is equal to delta naught times f prime. Delta 2 is equal to, let's write that out. So i.e., delta 1 is delta naught times f prime of x star. Delta 2 is just delta naught times f prime of x star squared, and so forth and so on. Each time you go one iterate higher, you just end up multiplying by f prime. And so therefore, delta n, you'd rationalize is delta naught times f prime of x star to the power of n. Oop, I realize you can't see this, but when I teach, actually there's a big light on my right here, which is why I'm always a bit nervous about stepping backwards. Okay, so, and this thing here you know converges to 0 if this quantity here has an absolute value. So this will tend to 0 if the magnitude of that quantity there is less than 1. And it tends to infinity if the magnitude of that quantity there is greater than 1. And there's your stability and instability. Okay? Okay, good. So we've established a criterion for stability. You just have to check the absolute value of the function at the fixed point. This should really be x star. Okay, good. Let's talk about stability for the case of 2 cycles. So this is a question that someone had asked in the chat. How do I tell that a 2 cycle is stable or unstable? Well, one way to check is that you just treat the 2 cycle itself like a fixed point, right? So this is item number 4, and item number 5, item number 5. 1, 2, 3, 4, 5. So to check the stability of the 2 cycle, you can just define g of x to be f squared of x. Or again, this is f of x. And the point is that you'll be stable, the same criterion would apply. So i.e., check if g prime of x is less than, or it's greater than or less than 1. But how does this actually work? How does it work if you have 2 points? You have to check both points? So if you have a 2 cycle, you have an x1 and an x2, and you go back and forth between the x1 and the x2. And the question is, do you have to check both? Right? So note, if g of x, if I take the derivative of that function, then by the chain rule, this is just f prime of f of x times f prime of x. So let's suppose that we have x1 and x2 are this should rather be is 2 cycle. The 2 points are part of a 2 cycle, or the set is a 2 cycle. And by definition, this means that x2 is equal to f of x1, and x1 is equal to f of x2. This I'm going to do quite quickly, by the way, just because actually this is exactly one of the homework problems. So I'm giving you a bit of a hand for one of the homework problems. Then g prime of x1. Suppose I want to check stability of this g function. I want to check the gradient of that function x1. This, by this formula, is f prime of f of x1 times f prime of x1. But I know f of x1, this is just x2. So this is f prime of x2 times f prime of x1. And had I done the same calculation for g prime of x2, I'd get the same thing. So what do you conclude? Well, you conclude that it doesn't matter whether you check the gradient of g at x1 or x2, you get the same value, and so you only have to check one of them. Okay? And so I'll give you a reference here, so see problem set 1. I think it's question 1. So this is part of question 1 is to get you to investigate this property. In question 2, it's asked you to generalize that property to n cycles. Okay. I had really hoped that I would get into item 6, and I won't be able to, I'm afraid, because we only have 5 minutes left. But I'll explain to you in words what it is, and then we'll cover it on Monday, and then you'll still be able to. So at this point, you'll be able to do question 1 and 2 from the problem set, and then question 3 uses this item 6. So let's talk about this question of stability. How do you define stability? And the point is that stability, even for the question of a point, is a point stable or not? Never mind the question of a set. Is a set stable or not? That's more complicated, right? But that's something that we're going to explore in this class, in this course, in this module. The question of stability is a little bit complicated because if I say that a point is stable, then what I might mean is that actually if I start near the point, I converge to that point. That's what I mean by stable. If I start slightly further away from it, I eventually converge to it. That is something that I might say is stable. But I also might mean that if I start near the point in some manner, then I remain near the point. So I don't have to approach the point, but as long as I remain close to the point, I'm stable. These are two possible definitions of stability. And in the notes, it defines this as either Lyapunov stable or quasi-asymptotic stable. And a point is then defined as asymptotically stable if it satisfies those two definitions. Let me give you an example, just in terms of a picture. Suppose that you have a dynamical system and then you plot the iterates, xn versus n. And suppose that my claim is at this point x. My claim is that x is stable, right? Well, what might happen is that, now, this should be a fixed point in the system if it's a single point. And so if I were to start at this value of x, I would just remain at that value of x. That's a bit boring, right? But what might happen is that I start at a point y, which is very, very close, a distance delta away from x. Okay? And you run your code, you run your dynamical systems forwards, and what might happen is that the system then looks like this. Okay? I've drawn it with a curve here, but in actuality, you'll have points, okay, at discrete values of n, but it's just easier for us to draw a curve. The notion of stability you can define for functions as well as for continuous functions as well as for discrete functions. So in this case, if you start sufficiently close to x, you'll always remain close to x. In particular, you remain within a bubble. Let's call this bubble epsilon. There's an epsilon over 2 distance if you like, or delta over 2 distance. Let's call it epsilon just for now. And so my criterion of stability is that I claim that a point is stable, and all I have to do to show it is to show that if I start sufficiently near that point, if I start sufficiently near x, I'm always going to remain near that point. This is what's called Lyapunov stable. And we'll give the exact precise definition on Monday. But in the other situation, suppose that I claim that this point is stable. I've not just told you how it's stable. And suppose that I start near that point, my y starts near that point, and then as soon as I run the simulation, as soon as I run my system, it goes away from that point. That doesn't look very stable, but then afterwards, if I wait long enough, it tends towards that point. So in this definition here, the challenge then, so I claim to you that my point x is stable, and you say, oh, I prove it, right? Show me that you're always going to be close to that x. In order to prove it, what I would have to do is show you that if I start sufficiently close to the x, then eventually, after a sufficient amount of time, I'm going to then be a distance of epsilon within the x. And so the definition of this will be a definition that involves some n. And you say that for a given epsilon, for a sufficiently small delta, there exists an n sufficiently large so that if you wait for long enough and you're above n, capital N, I mean, then you're close to that. This is called quasi-asymptotically stable. QAS. You can call this LS. Informally, we say this starts near, stays near. Lyapunov stable means starts near, stays near, while this eventually tends to. This is the definition of stability. Lyapunov stable, a system which is Lyapunov stable about a point x. If you start sufficiently close to x, you'll always remain close to x for all time. Whereas a system which is quasi-asymptotically stable at the point x is such that first, after a given amount of time, possibly very long amount of time, you'll eventually be arbitrarily close to that point, as long as you start close enough. If you have those two definitions together, then you have a system which is asymptotically stable. Okay? All right, Monday we'll write down the exact definition of those two concepts of stability. And before you go, I'm just going to flash up here we're going to just put the problem set questions up here, just so you can see. And I just want to always end the Friday lecture with a guide of, you know, what you should be able to do now in the problem sets. Okay, so this is now the problem set which is available online. You'll see question 1 is about the logistic equation. Question 2 is a proof about n cycles, generalizing one of the results that we showed just a minute ago for g. G is equal to fn of x. And the third is a stability question. You're asked to draw cobweb diagrams of these different functions and then to comment on their Lyapunov stable or quasi-asymptotically stable. Because this question 3 is in fact informal, you don't have to prove anything, you just have to draw lots of pictures, you can actually do it at this point. You don't actually need our technical definition on the Monday. In question 1, it's just a walkthrough of many of the properties of the logistic diagram that we've already covered. Okay? So that's about it for the Friday course. For the Friday lecture, I always get confused, lecture, course, module. For the Friday lecture, again, I'll hang around for a couple minutes. Any questions, you can just write in the chat, or of course just get in touch with me otherwise, and have a good weekend then.